Okay. I want to start ideally with a framework that starts a little more abstract. We'll hang the ideas of money off of it. But one of the big issues is making sure that you understand all the symbols we're going to use and the way we treat them. And in a lot of cases, we make stuff up for the way things work. There are justifications that we can go 1,000 miles deep that are completely unnecessary for this course. I just need to make sure we know what the hell is going on with the ideas. So I needed to start with an overall gross disgusting idea. The hell's a real number? Oh, wow, man, it's imaginary. No. Historically, we start with the idea that you count, right? 1, 2, 3, 4, 5, 6. About 700 AD, a mathematician is talking about the idea of emptiness, of a lack of quantity. And this Indian mathematician, I'm gonna murder this name, Arabiyata II, I think, has this idea that I can represent a lack of something with a cycle. We translate this word badly, you get zero, zephyr, and from that we get zero. And he says, oh, I've got this idea about using this symbol to mean an empty position. And that means that we are, no, it's coming this way. It's coming this way. From that and the Chinese, we get people writing different colors to represent numbers that are going out and numbers that are coming in. When I get paid something, when I have something, I write it in black. When I don't have it, when I put it out for someone else, I write it in red. We still use this today as the idea of a business. Being in the black means money's coming in, and being in the red means money's going out. Comes from Chinese income. The development of negative numbers is also an idea. And then fractions goes all the way back to Greek antiquity. And then somebody said, there are numbers that don't fit, that aren't fractions, but that are still real measurements. And the historical version of this is given to Pythagoras, who draws a triangle, one across and one up. And the diagonal length is the square root of 2. And you can write an argument in mathematical Euclidean terms that shows that that number cannot be written as a fraction. So there are numbers in our universe that are not fractions, that are not whole numbers, that are weird. But if I take all of that collection, that's what we mean by a real number. They can represent real lengths. They can represent objects that we work with. So when I think about operations on real numbers, 99.99% of the time in this course, I'm working with decimal fraction. But there are things out there like pi, third, 2, and these weird numbers that have uses and still work for us. There are a couple we will use in particular later on in the semester. One of my favorites is the number E, credited to Leonard Euler. We'll deal with that when we deal with power. But if I'm dealing with real numbers, I don't want to have to pick a number as an example every time. So frequently, we'll represent a number as a letter. Hey, it's not the alphabet in the math, and everybody freaked out. It's just a box to put stuff in. So when I pick a number, I'll write a letter for it because I don't care what number it is. If I do care what number it is, I'll talk about, hey, maybe this number can't be 0, or maybe this number has to be positive, or something like that. But most of the time, we represent a lowercase letter just to be a number. This is the fault of Pierre de Fermat, who said letters at the end of the alphabet will be things we don't know, and letters at the beginning of the alphabet will be things whose value is known but not specified. So A is some number I'm going to use. But when I write an equation, I'm going to put X in for the thing I don't know about. Letters at the end for things I don't know. So almost all of the familiar operations, adding, subtracting, multiplying, dividing, I don't use a symbol for multiplying when I'm writing letters like this. They're just put next to each other. There are lots of options for multiplication. We will sometimes write that little cross symbol. It's not really an X. I don't like using that because it looks like an X to me all the time. Some people will use a little dot. Again, I don't want to do that very often unless I have to emphasize the multiplication part that's going on here for some reason. Because those symbols also have other meanings in other fields. I don't want to put them either. So most of the time I'll just write two things together. But multiplication is repeated adding. That's all you're doing when you multiply, right? If I write 2 times 5, I have to put a symbol between those, otherwise it looks like 25, right? I can either think of adding 5 twice, or I can think of adding 2 5 times. Piece of cake. By the way, when you multiply by a number by itself, what do we call it? We usually write it differently.
An exponent.
Not any exponent, but in particular, squared. Do you know why we call it squared? You make a dot and there is a square. That's it. They're actually called figurate numbers. And so when we first started doing this, we literally drew out a rectangle for multiplication. 2 rows of 5 dots, 5 plus 5, or 5 rows of 2 dots. It works. But that's why when we do exponents, I use P for power. I can think of that as repeated multiplication. So when we think about 3 to the second, that's 3 times 3, 2 times. But I can do 3 to the third or the fourth or the fifth. I can do 3 to any power I want. I mean, some of these numbers are easy to deal with, right? 3 squared is easy. But, 7 to the fifth, I'm in trouble. You have a calculator. You should find it. If you have your laptop open in front of you, there's a calculator app. Pull it up. What's 7 to the fifth? The calculator app, you can get the access from the Launchpad in the MacBook. Behaves just like a calculator. What is 7 to the fifth power? 16,807. An apocryphal story. When anybody play chess? Chess is a war game. You've got your army, they've got their army, your goal is to make them surrender. There are 64 squares on chessboard. Chess is a Persian game. It originates in Persia. By the way, the pieces originally have very different names. vicious. How vicious. They move diagonally. And if you look at the picture for the piece of addition, it's got two diagonal lines on it, indicated with diagonal, and it looks like it's got one of the pointy heads. The original Persian piece is an elephant. Those are tusks. And that is the howdah which you ride. Has nothing to do. The English changed the game to make it more simple. But chess is introduced in Persia. And the Sultan is so thrilled, so happy. He says, I want to reward you for bringing me this game. How can I reward you? And the chessman goes, I would like grain so that I can feed my family and grow fields. Let's put one piece of grain on the first square, and 2 on the second square, and 4 on the next square, and 8 on the next square, and 16 on the next square. How big is the chessboard? It's 8 by 8, 64 squares. What the is that number? First of all, what's this mean? Unfortunately, no, it doesn't mean an error in this case. It is an exponent. In particular, it's an exponent that's a power of 10. So this means that what you really want to do is take 1.8 whatever and multiply it by 10 raised to the 19th power. Every time you multiply by 10, you put a 0 on the end of the number. So this is 1, 8, 17 zeros. Okay, hang on a second. A million has 6 zeros. A billion has 9. A trillion has 12. That is 18 million trillion. If you did that in pennies, that's more than the entire domestic gross product for this country for its entire history. The head vizier walks over to the Sultan and says, you owe him every grain in Persia for the last 3,000 years. They didn't get that away. These numbers get huge very quickly. So when dealing with powers, we'll often see numbers shortened like this. So that's 1.84 E19 means 1.84 times 10 to the 19th. Yes, ma'am. Oh, the 17? Because I said 184 and then 17 more. So a total of 19 from where the dot is. I have to move it over 19 times. I moved it over 184. Just gave up on the rest of the numbers. Or is that not the 17 you meant? Okay. Okay. This idea will come back to us of dealing with exponents as we think about payments and interest. So I can add, subtract, multiply, divide, use powers. If I write an expression down, I need to know what order to do things. I am sure you have all seen on social media memes about, well, what's the answer to this? And they use some garbage looking expression. I hate this. For 2 very different reasons. The first is, this is bad writing. It's like trying to translate directly from German to English, where you get a word that was formed in German by gluing 18 other words together. So you translate it as car, man, drive, thing, to, east. Yeah, that makes perfect sense. No. The second reason I hate this is because we made it up. In the 1300s and 1400s and 1500s, as Hindu Arabic numerals are becoming the norm, all the math before that was done in Roman numerals. I want you to imagine doing your timetables and exercising things. I'd rather throw some up. For the record, before that, if I go back further, in Mesopotamia and Babylon, we didn't use tens, we used 60s. So the times table went from 1 to 59, and we still do it today. The only reason clocks from 60 was because the Babylonians left 60. But when I would write in the 1400s, I could write this to mean do the multiplication first, then the division, or do the division first and then the multiplication. I had to write it out because before these numbers were popular, you wrote it all in words and numerical expression. In Roman numerals, you wrote out the words. Take 16, multiply by 5, and divide by 2. Would be written and divide the result by 2 if I wanted to make sure you did the multiplication. Or it would be written first divide 5 by 2 and then multiply the result by 6. You could say it in English much more clearly. To get around that, mathematicians subsequent to about 1400 would group things that they wanted done first with parentheses and brackets and braces and whatever else we symbols with it. This stuff, do this stuff first. And if there were no symbols or braces like that, you worked from left to right. We made it up. So I don't care what sort of abbreviation you've seen. Anybody know what either of those are? What is it? What does it represent mathematically? Parentheses. Exponents. Multiply and divide, add and subtract. We made it up. It's been stuck this at, by the way, B is the British version because they would call parentheses called braces. So braces, exponents, multiply, divide, add, subtract. But these two are given equal priority. So you simply do them from left to right. Whichever one you run into first, you do. But you always do the stuff inside the parentheses first. You do the exponent immediately after that, whenever possible. But we always work left to right. Some parentheses are implied based on location, but that's not always nice. Now, some calculators allow you to type in this expression exactly as written, and it will remember order of operations for you. And some calculators are dumb and don't allow order of operations. And some calculators are built to prevent you from ever having to think about order of operations by the way you put stuff into them. I have a calculator that doesn't type equal sign because it doesn't allow you to type in an expression that is equal. You have to tell it, okay, take these two numbers, add them. Take these two numbers, multiply them. So you have to tell it what to do after you do it. By doing so, You always say, oh, these numbers, this is what you're gonna do to them. So there's no which way do I do it? You built that in before. Hewlett Packard makes a lot of those. They're really geeky calculators. How do I do this? Walk me through the arithmetic. Yes, ma'am.
This is like to assume where parentheses are, right? See, I think the parentheses would be over the 4.5.
That is actually our multiplication symbol again. So yes, I'm multiplying before I do the adding or subtracting. And 4 times 5 is easy, right? So yes, there isn't an obvious set of parentheses, but my order of operations intent is that I would multiply before adding. And now, left to right. 33 minus 20
13,
plus 8.
21.
Ta-da! The problem becomes, again, implied parentheses. So here's the one that always annoys people. I have not seen this expression written this way in my text. What I instead see is division not written with that arbalist symbol, but actually written where the expressions go where the dots are. So instead of writing this, what I see is this. See how the division symbol with the dots in place means this expression goes on the top, this expression goes on the bottom. So I can literally say this symbol is supposed to be this one. And that's where division is. I like it. Somebody give an answer. So, again, division would be done before adding and subtracting, but there are implied parentheses here in this expression. So I end up with negative 20 plus 4, negative 2 minus another 6, negative over negative becomes positive, 16 over 8 is 2. And over here. You're allowed to use your calculator. You don't have to do this crap in your head. Negative 7 squared. I'm a sneaky mother. I'm a sneaky mother. Say it again. Negative 49. The exponent gets done before because there are no parentheses there. So the exponent happens before the multiplying by the negative 1. And that's really what this minus sign is. It's a multiplier. Or if I wanted to think of it as subtraction, it's 0 minus this result. So I have to do the power first. If I wanted to do the square of negative 7, then I would have to write it that way to tell me to multiply the negative by the negative, thus giving me positive 49. Talk to me. A power is a version of repeated multiplying. So that's all a power is short for, is to multiply however many times. So when I say this, I'm doing multiply this 7 by itself. The issue is that I can make this expression as complicated and as recursive and as deep layered as I want to. I have not made up a single one of these. I have stolen them all from our textbook. And this one came from there too. Mother. If I'm going to follow our quote made up rules, I'll do what's in the parentheses first. But within each set of parentheses, the numerator and the denominator of this is another fraction. And then I have to say, okay, well, ignoring everything outside of that, what do I do there? So I need to make it one number on top, one number on bottom, then figure out what the division is. One number on top, one number on bottom. And I can do the same thing down in the bottom of the big fraction. 6 minus 3, 1 minus 4. And now I can do those divisions. 8 over 4. But there's a minus sign in there from the negative on the bottom. So negative 2, right? Plus 4 over negative 2 plus 3 times. Again, there's one negative in there, so the answer in this fraction is negative 3 over 3. Yay. By the way, the idea that one would multiply a negative and get another negative, multiply a positive negative, why do I do this sort of thing? I want you to think of negatives in my number line, right? I have positive numbers to my right, negative numbers to my left in my number line. So when I multiply, I turn around. So what happens when I multiply again? Negative times the negative puts me back on my positive side. So the flip twice. And multiplying by a positive thing just moves me. It doesn't change my direction. So multiplying a negative by a positive means I'm over here to begin with, and I don't change. I'm still over there. So multiple powers come before multiplying. So I got to do this power. 16 minus 2 times minus 2 plus 4. Negative 2 plus, 3 times negative 1 becomes a negative. You could write plus a negative 3 if you wanted to leave that in the parentheses. That's fine. Multiply. And then I will have all the top to add and all the bottom to add. And then I'll end up with number over number. 16, what happens here? Say again? It flips and it becomes a 4. And it becomes a positive 4 because I've got a negative and a negative. And then another 4. This didn't have any multiplication in it, so I can leave that like it is. Okay. I'm adding and subtracting. I work from left to right. 16 and 4. And another 4. Negative 2. Minus 3. Negative 5. Plus 9. -5 plus 9 is the same as 9 minus 5. So at 9 minus 5 gives me a 4. 24 over 4. Yay. The reason we establish these hierarchies, what to give priority to, is so that the stuff I write can be less confusing. Because imagine trying to write this expression as a sentence. If you wanted to write a sentence that said, this is what I'm going to do with these numbers, we'd be here, it'd be like this big, right? That's a sonnet, not a sentence. So the goal is to simplify the confusion that would result from not having this. Questions? So the next time you see one of those memes on Facebook or Instagram or wherever your social media leads you, you can say, this is an ill-formed expression, go away. I normally use this calculator. I've had a variation of this calculator for about 30 years. It's the one I know the best. A calculator is a dumb machine. The first calculator I ever used was beads on a string. Abacus. That device is about 3,000 years old. And as arithmetic goes, it works really well. But it doesn't work in tens, it works in fives. So it's a very different type of calculator. Calculating devices are there for you to offload something that is tedious in your head. This was annoyingly long. If I could write it into a calculator cleanly, I'd just let that do it. But I have to know what's going on with that expression to translate it into the calculator. This calculator is stupid. It does exactly what I tell it to. It is not large language model. It is not AI. It is not any of those things. They're getting to the point where they can do these expressions. There's an app called Photomath. If you take that app, point your camera at this, it'll spit out the answer. But getting to that point took about $5.5 million of R&D. I like the 3-pound calculator between my ears. Questions? One of the issues we have in math versus the rest of the world, us East tough. And in a very real sense, the hardest part of any math class is not necessarily the symbol manipulation, it's the translation. Here's a paragraph of information. What calculation do I need to do from? What information in there is useful, and what words tell me what to do? Who's taking or has taken a lab science? Okay. Who will take a lab science? Who cooks? Isn't a recipe an easy read? Exactly. What's brunoise mean? How does saute different from fry? I can burn water some days. On the other hand, some days I cook really well. But The whole statement here is that there's an assumed language, assumed base of knowledge. In cooking school, you go to culinary school, they will teach you all those different cuts of meat, how to handle your knife really well and not cut fingers. Do a good stuff. I need to do that here as well. And in the lab sciences, I talk about, I don't know if I'm in chemistry, I talk about dilution factors. I talk about molarity, I talk about concentration, and those mean particular things to do to my chemicals, to write out reactions and reagents with each other. When I start to write about mathematical sentences, I need to turn English into geek speak, turn it into the set of symbols that make a comprehensible and usable idea. And sometimes these are deliberately, annoyingly rigged to sound dumb as hell. But a lot of it is just the idea of translation. Every one of our arithmetic operations has a word that goes with it. When I'm adding, I can use the word sum, I can use increase, I can use taken with, I can use the word plus. All of these become algebraic expressions. Advantage. Adding is order independent. If I take 5 and 7 and add them together, doesn't matter whether I do 5 and 7 or 7 and 5. On the other hand, fraction is order dependent. So 17 less than y means I'm taking the 17 away. But 17 less y, if I remove that word than, 17 less y means 17 minus y. Whereas 17 less than y means y minus 17. $17 less y. Take y away from it. And the only difference is one word. That's not hurt. So I need to make sure that I can translate from one to the other. Subtract 3 from A, so from A, I take away the 3. Difference of P and Q. Now that's problematic to me, because I just said the order matters. And is the difference of P and Q, P minus Q or Q minus P, which one comes first? Well, in that case, it's going to be the order they wrote it in. Left to right. Because that's the way we write English. I suppose if we were doing this in Chinese, we would be top to bottom. Or in Arabic, we'd be right to left. Again, multiplication, factors, product. Just naming the type of ratio we've got, twice something, half of something, a quarter of something. Again, I go back to my recipes. I want to double or have a recipe. I need to be able to do this maneuver. Division. Again, division matters. Which one's on top, which one's on bottom makes a difference. 1 over 2 is a small number. 2 over 1 is a larger number. So I need to know which is the top. 78 divided by P is 78 over P. I'm dividing by the P. Again, I don't like using this Arbalist notation. Whether you use a diagonal slash for your fraction or a horizontal slash is really a matter of space saving. But if you're using a compound denominator, if you're dividing by more than one thing, if you use the diagonal, you need parentheses around those. Otherwise, you should use the horizontal and write them all out, like we did in that example we were just looking at. Equality and inequality. The word is gets thrown around in math a lot as an equal sign. X is 7. Oh. I'll use the word equals much more often. Less than. Your alligator eats the bigger thing. This one is bigger. This one is bigger. So I'm reading from left to right. That first expression says X is not less than. See how it's slashed through? But if I want to read it as, what's the opposite of less than? More than or the same as. Right? Just means not less. I could be the same. So this symbol is X is bigger than, and that extra line on the bottom is an equal sign. Less than, greater than, or equal to Y. At least. Well, if I'm at least, I could be the same as, but I might be bigger. The phrasing is the problem part. Page 19. As we progress to different kinds of expressions and equations that we want to use, we will run into the fact that we need larger sentences and more complicated ideas to deal with them. Because again, in English, the sentence may be big, but the expression might be really small. I'm going to butcher another one name again. The Arabic mathematician Al-Khwarizmi. I'm going to even, there are 4 other names in the middle there. Al-Khwarizmi is last. Wrote a book called The Method of Completion and Reduction. The word in Arabic for method is al-jabr, which became al-jabr, which became algebra. A-L-J-A-B-R is how it was transliterated. And when they were translating Arabic to, at the time, Latin and Greek, they wrote the literal. And so al-jabr became algebra. Prior to the introduction of symbolic algebra, before Al-Khwarizmi, he wrote out words meaning expressions. The hell's that? What's the easy expression for this? Okay, wait a minute. The sum of 25 and. Oh, the sum of 25 and. And what? Seven is some number, right? But that and, I need to be careful with that because it says here product. So I could just write multiplication. I could say 25, the sum of 25 and a product means multiply in the middle, of 7 and some number. But notice that that extra symbol in there doesn't have to be there because we can just write multiplication as juxtaposition when I can see the two things are different from one another. Again, I'd like an expression that represents this idea.
5x minus 7.
5 times some number is decreased by 7. Wonderful. Whoops. The difference. Takes me longer to write it out. The difference of 50 and the product of 3 and some number is no more than 20. The difference of, what do I need to write? The word difference means subtracting something. The difference of 50 and, the product of 3 and some number. The product of 3 and some number. I don't know what number it is. Use anything I want. Is no more than. Is no more than 20. So there's a 20 here, and I'm doing a comparison. Less than or equal to. It can't be bigger. It's got to be less than or equal. I have just brought in a word you've not seen before.
The hell's an integer?
Integer is geek speak for a whole number. Either positive or negative or zero, but a whole number. 3, 17, 143, but not 2.6 or square root of 7. It's got to be a whole number. So, what does it mean to have 2 consecutive integers? But more than that, what's the word consecutive? Heard a mumble. Back to back, right? One immediately after the other. So if I have a number, the consecutive, it will be the next one in line. What are those different by? 1. So I need some number, and then I need the next one. What's my expression for some number? A letter. What letter do you want to use? S. So I'm going to use S, and because S's and 5s always look the same to me, I'm going to write a cursive S. S. And the next one. So what's the next one? S. And one more. It's a number. I can't use the next letter. I want to make sure it's the next number. If I used T, it could just be some other number, right? It might be a completely different number, but I know it's got to be one bigger. So the next number is one bigger. S, and the next one is what symbol? What symbol is?
Equal.
An equal sign. Is 95. And my bad handwriting is the reason I don't use real capital printed S's, because that 5 looks like an S. Translating English to geek and geek back to English is important. We're going to do the reverse. I'm going to give you a sentence and ask you a symbolic sentence and say, read this to me in words. Because you don't walk up to 7 people and go, hi, 7x plus 13 equals 42. They're a Martian, shoot them. Nobody speaks an equation outside of the classroom. So we want to communicate in English. I need to be able to translate back. More to come on Friday. See you all then. If you came in late, my sign-in sheet is. You go, you still have, so if you came in late, you make sure you get on the sign-in sheet. I will see you all on Friday. Thank you.